Good morning. My name is Jacob Jørgensen, and I will be entertaining you for the next 20 minutes or so with respect to a project I'm involved in called the Femern Fixed Link project. And if the technology would... There we go. I'm having difficulty sharing my screen here. I'm sorry. I don't know. Can you see my screen now? No? No. Let me just see if this works.
Share from outside. Jacob, let's share from outside.
Can you share my Chung, can you share my presentation? Because I for some reason it won't let me share the screen. Maybe that works. Let's see. Let's see if that works. No. It
You can see the screen. Yes.
Can you share my presentation, Chung? Would that be an option?
Jacob, please reduce the volume because it's a little bit louder here.
Okay, Jacob, please speak. Okay,
There we go.
Jacob,
Fantastic. Thank you very much. So again, good morning, and sorry for that technical problem. My name is Jacob Jørgensen. I'm a Danish lawyer, and I'm going to speak to you about the Femern Fixed Link. This is an 18 kilometers immersed tunnel linking Denmark to Germany. If you could switch to the next slide, please. So the fixed link you'll see at the bottom there is linking the island of Lolland, which is the southern island of Denmark, with the northernmost island of Germany called Femern. It's a part of at least one other fixed link, which is the Øresund link you'll see just above, which is linking Copenhagen to Malmö in Sweden. We also have... There we go. We also have a third asset in the company I work for called the Great Belt Bridge, which is linking Zealand to Fyn in Denmark. Yeah. And if you could switch to the next link, please, the slide, please. So the Femern Fixed Link is essentially aimed at facilitating the transportation of goods by rail from mainland Europe through Scandinavia up to Sweden, Norway, and Finland. You can see the numbers there. If you as you'll see in a moment on the other slides, the link will have both a train or rail connection and road tubes. The road will take about 10 minutes by car to cross, going at 110 kilometers an hour. By train, going at 200 kilometers an hour. It's a 7-minute journey. and that will cut the transport time from Copenhagen to Hamburg down to 2.5 hours, saving approximately 160 kilometers. And the next slide, please. So it's currently the longest immersed tunnel of its kind in the world. It has, as I said, 18 kilometers in length. The tunnel elements, which you'll see in just a moment, are manufactured at a factory in Denmark. That's the top circle you'll see there. That's the harbor and the basins where we push the tunnel elements into. The construction budget is 7.1 billion euros, and it will be 100% user financed. And next slide, please. It will become part of the so-called TEN-T, or 10th, the Trans-European Transportation Network, which, as you can see, will link Sicily down south to Norway, Sweden up north. So it is currently sort of the missing link in that massive rail connection from the extreme south of Europe to the extreme north of Europe. And next slide, please. So the tunnel consists of 89 tunnel elements in total. There are 79 so-called standard elements. Oh, one down, please. Slide, please. Yeah, there we go. So the standard tunnel elements are 217 meters in length. They are 42 meters wide and 9 meters tall. In addition, there are 10 so-called special elements with basement compartments, and you can see that they are shorter. They are 39 meters long, 47 still wide, and 13 high. And the height is because of that basement compartment. And next slide, please. There you have an illustration of a standard element. You can see that it is immersed into a trench that's been dredged into the seabed. You can also see the 2 road tubes to the left, and the train, the rail, is in 2 tubes to the right. You can also see there's a gallery between the 2 road tubes for servicing the tunnel. When immersed into the trench, as you can see, there will be a need to lock in the element. That's done with the lock-in fill. Oh. That's done with the lock-in fill. You can see illustrated there to the right. That will prevent the tunnel elements from moving in the trench as a result of current and underwater waves. Then there's general fill on top of that, and finally there's a protection layer which will cover the tunnel elements totally under the seabed. So next slide, please. That's another illustration of the standard tunnel element, as you can see there. Perhaps a little bit more clearly the road tubes, and to the right the train rail. And next slide, please. Next slide, please. So some interesting facts for you. The amount of rebar that we're going to use for this tunnel corresponds to 50 Eiffel Towers. We have dredged, or rather our contractor FBC has dredged 15 million cubic meters of seabed, which has been used to expand the Danish southern coastline with a total landmass of 2.3 million square meters, which is slightly bigger than the state of Monaco. If you try and click the link, Chung, there's an interesting video which I think we might have time for. Don't know if that works. If it doesn't work, maybe it does work. There we go. Oh, some Vietnamese commercials first. You can skip that. There we go. There we go. Thanks for that. Turn to the next slide, please. So the train connection, which is probably going to be of interest to some of you, this is not a high-speed train as defined in under European standards. However, the train connection between Denmark and Germany that this tunnel will cater for has many of the similarities to a high-speed rail project. I will try over the next slides to give you an idea of how the design of the train or the rail in the tunnel is done. So if you go one up, please, slide number. There we go. So the train is a 200 kilometer operating speed. A connection 200 kilometers an hour will present more or less the same challenges as with a high-speed rail going through a tunnel. So I'll be trying to illustrate the tunnel-related issues when it comes to the design of the Femern Link train connection. The design is largely dictated by European legislation or EU law. First of all, we have the Interoperability Directive. That's a directive from 2016, which establishes the framework for interoperability of the European rail system. You may not have that same requirement in Vietnam, given that, as I understand it, your project will be from north to south in the same country. But nonetheless, the interoperability here, and to the extent you have differences in your regions that your train line will go through, this may be of interest. So the Interoperability Directive regulates what you can see there, the track design gradients and station platforms, rolling stock, train design aerodynamics, crashworthiness and passenger safety, pantographs, voltage standards, control commands and signaling, which is a huge issue, and finally some rules on persons with reduced mobility and how they can access the platforms. Next slide, please. And next slide, please. Thank you. The next ones are also of key importance when designing in one up, please. Slide 11, please. Slide 11, please. We'll just go one up, please. No, slide number 11, please. Just click on 11, please. Thank you. So the next one, a key regulation, also Railway Safety Directive. You undoubtedly have similar rules in Vietnam. This one is also from 2016, number 798. It establishes safety requirements for train design, including crash resistance, emergency evacuation systems, and fire protection. Then we have environmental and noise regulation that's spread over the regulation I mentioned there, 1304 from 2014 on noise, and the 2011, that's the Environmental Impact Assessment Directive, which is more of a general regulation that one has to comply with when doing infrastructure projects. We also have a soft law in the form of EU Green Deal and Sustainability and Smart Mobility Strategy, which encourages energy efficient design use and so forth. Then we have a specific on passenger rights, maybe not so interesting for the purposes of your project. Next one, please. These are interesting, I think. Fire safety and crashworthiness. There are two standards that are typically in play. The two I mentioned there. The first one on crashworthiness standard sets crash energy absorption requirements, and the next one on fire safety. Then there's one on electromagnetic compatibility. That's in a directive you see there from 2014. It ensures that high-speed trains do not interfere with other electrical systems, such as signaling and communications. Then we have a standardization and certification regulation, as I mentioned there. In Europe, the European Union Agency for Railways, or the ERA, have to certify the trains before high-speed trains, including before they are put into operation. And according to contracts, compliance with EN and ISO standards are always required in practical life. Next one, please. So looking at the tunnel-related design issues specifically, there are two that I just picked out here. One is on the size of the tunnel that will have to correspond to the train speed. If you go into a tunnel, I've been told by the technical guys in my organization, with too high a speed, the sonic boom will expose the train, the rolling stock, to loads that they're not designed for. So there has to be a correlation between the size of the tunnel and the speed of the train. The other one is well, it's related. It's on pressure loading when going into the tunnel, because of the air pressure that the rolling stock is exposed to. You'll have to basically make sure that your procurement of the rolling stock is done and designed in a way that it can please. So looking at the contractual regulation, what I got out of the little I understood from the previous presenter, in the logic form of contracts and the ones we have in our project, they're very, very similar, almost identical. So key elements here. In our project, the rail-related parts are split into the packages I mentioned here. First, the civil works, that's the casting and immersion of the tunnel elements. As you saw, it was there are 2 tubes for trains in each direction. Then we have the so-called TTC, or the train track and itinerary package. That's the track and the power that will energize and allow the train to move. And then finally, we have the TPS, which is the tunnel power supply. This is a transformer station that will supply power to the entire tunnel, but also including the train. Now, the contractor is responsible for so this is an EPC package, and the contractor is responsible for the design and compliance with technical standards for interoperability, etc. So basically, all what I just mentioned in the previous slides will be for the contractor to comply with when designing the train packages. Next slide, please. Like you have in the logic form, the usual clauses there: rely upon information. The employer will provide information that the contractor can rely upon when designing the package. We have a modeling in our contract. All parts of the design must be modeled as per the BIM specification. This will facilitate especially managing interfaces to other parts of the project. So everything is done in BIM. We have rigorous testing criteria. The adequacy of those are the employer's liability or responsibility. We have the usual clause on ground conditions. The contractor must check the information given and design accordingly. And if the contractor sees something that is going to give rise to issues, he must notify the employer. Same as you have in just about any other large EPC contract, whether it's based on logic or FIDIC, it's the same. Compliance with technical standards as at the base date. If those standards change over the course of the project, this can give rise to variations or variation claims from the contractor. And next slide, please. Other issues here, availability, there are the amount of outage there we go. The amount of outages you can have per rolling stock is defined in the contract. Maintenance guarantees go hand in hand with the availability. Safety and risk assessment is regulated. Interoperability, a key issue because the train in our project goes from Denmark to Germany. And finally, O&M training, all that is regulated in detail in our contracts. And next slide, please. So testing, there are provisions on factory acceptance tests. So that's before the hardware, so to speak, is sent from the factory, from where the EPC contractor has purchased it. So basically at the supplier's factory, the goods have to be tested. There's a site acceptance test. So once the goods are shipped to site, there will be a test regime in place. Then there are tests of the works on completion. So once the tracks are laid and the catenary is in place, there'll be a test done in order to establish whether the works are complete. And then after completion, there are further tests. So once during commissioning, so once the tests for completion are done, during commission, and once the system can be operated in a stable manner, there will be the test I mentioned there, testing for operational integration before the works are put into commercial operation, and finally verifying that the achievements of the availability guarantees are met. So rigorous testing in place. And next slide, please. So in Europe, we use these standards for testing the after completion or after taking over. The ones I mentioned here are mainly aimed at establishing the functional safety. And then the next slide, please. There at the bottom, that link will link you to the ones I just mentioned, the RAMS tests. And I also have two others here. If you want a summary of the EU rules, that article I mentioned, the first link, is useful. And finally, I've added the ICOM report that came out 3-4 days ago, which is the playbook for high-speed rails, which might also be a source of inspiration. And that is all I had for you this morning. So thank you very much for your attention, and enjoy the rest of the seminar. Thank you.
Yeah, some difficulty in the network. So next, I would like to invite the chat team from Arab